I want to talk about background writings for a minute. You see, in database engineering, to build a database, we have this concept of documents or tables, graphs, right? But then internally, we really store these as pages. You know? Almost all database systems use the concept of pages, which is a fixed size, binary, area envelope. 8 kilobytes, 16 kilobytes, 32 kilobytes. And then we store the data that we want in these pages. And those pages are just binary bytes. They go to files as bytes. So if I want to page 0, I literally go, all right, seek to this file to position number 0. If I want page 1, that will become basically page 1 times whatever, let's say 8,000 is the page size, times 8,000 plus 1, and so on. So you do a simple mathematical operation to know exactly what page to pick, and you read exactly 8 kilobytes. That's how it works, right? And all files are stored like that. So you read and write these pages, and for efficiency, we store these pages in what we call the shared buffers. And this shared buffer is in memory, and it's called shared because all the processes of the database share this memory for efficiency, right? Because you need either multi-threaded or multi-processes to make your databases perform. Otherwise, it'll really suck, right? To have one single process do everything. So now we have this beautiful place in memory with all these pages for all these different tables. That's the beauty of this. The abstraction of a page is really nice, right? You have one thing and you can deal with that, right? Now, as you write to something, we write in memory only. We never write to disk. You might say, about durability. I'll come to that. You see, those pages are really fat. They're juicy. There's a lot of data in them. Imagine if every time I update a single row, single column in a row, right? We really need to update the whole page for checksum and all that stuff in memory. But we really have to flash the whole page, right? If I want to write it to this, which is really inefficient. You're writing this massive amount of data. So scientists said, all right, we're not going to it's enough to write in memory, but we're going to write these changes that we're talking about, that we actually made, to something called the wall, which is the redo log. And I talked about it in many other videos. And it tracks your changes. It's the transaction log, essentially. What happened, the source of truth, is done on that transaction log, on the wall. It's beautifully maintained. You can use that wall to replay all the changes from day one, if you have all the wall changes. So in case of a crash, you might say, I lost my pages that I wrote in memory, but we have the wall. So you go back to the final last known snapshot, or we call checkpoint, and you replay the wall from that checkpoint, and you're up to date again. So that's a beautiful design. You see, now we end up with pages in memory with changes that is out of sync with what is in disk. So that's why asynchronously with the OS, the OS does part of it. The database writes this on the background because, all right, let's because here's the thing: if you don't write at all these changes to memory, to disk, what will happen is crash recovery will be really slow, right? Because in case of a crash, the final known checkpoint will be so old that startup time will be taken most of the time to just recover, right? To write all these old wall changes that you've made for hours. So that's why you really need also to write this changes in on disk. And this is what is called, 5 minutes later, this is what's called background writing. So there is like a specific process or a thread or threads or processes that its job is just take dirty pages, write it to disk. Dirty pages, write it to disk. Just to make sure that everything is as latest as possible. So that's what it is. So background writing is a critical, I would say critical for crash recovery. But, right, so we need it. It's important to write this as often, but not really, like a life or dead situation. We can live without background writing. So you can configure all this stuff, AnyDB gives you certain configuration. It's called the maximum concurrent IO for those background writers. And it sets that, if I'm not mistaken, to by default 100 IOs, I believe. Yeah, you get 100 writes per second, So you can increase that to 1,000, 20,000, and it will basically allow you to write those faster. You can write the background, changes faster to disk. And you might say, this is actually attractive. Let me write those changes as fast as possible, especially with SSD, it will be really fast, right? But there is like a limitation when it comes to that, If you actually started writing things fast, then you are accumulating more and more changes, right? Because you're gonna write those, okay, there are some certain changes and you wrote them, and then more changes come and you write it again. So you're writing more, right? But then you're accumulating more changes. So you're writing very frequently. And SSD don't like a lot of writes. So it's actually better to delay those writes until you get enough nice, full of changes, and then you write them as once, right? Or reduce the maximum number of IOs you can do in a second. And this way it was like, I can only write 100 IOs. So all right, I'm gonna write a few pages. So while you did write few pages, and that's fine because we don't really need to write those anyway. We can still read them from memory. And in case of a crash, I'll take the hit, right? If you really just wrote those, the other dirty pages will have more chance to receive more writes. That is the power of this, It's a very interesting concept here. Postgres, unfortunately, I don't think has this IO configuration, but you can actually delay the background writer on Postgres. So that's the video I want to make today. Very quick while I was walking my dog. See you in the next one.